Hello everyone, and welcome to this video where we discuss some aspects of mathematics in research and physics as well. And often I try to put forward some articles that have not necessarily been kind of publicized a lot, that are not very well known by the public. Basically that's one of uh, those that we are going to see today. I think the video should be fairly short, but who knows? I tend to go on tangents quite often. Um, so the paper I want to discuss today is this paper. It's a quite old paper now by Verlinde, and the name is On the Origin of Gravity and the Laws of Newton. Now, the reason why I've chosen this particular paper is first because obviously the idea is very interesting. I'm sure some of you have heard of this notion that gravity and the laws of Newton could be emergent in some shape or form, but often it kind of stops there, and then there is not much kind of discussions about what are the physical arguments that are really brought forth. And so that's what this paper is doing. And the second reason why I want to talk about it is because a little bit like Susskind's paper in one of the previous videos, here this one, as far as I'm concerned, is fairly accessible. As long as we kind of accept some of the premises, let's say, of reasoning, then we can kind of move on to see how these things work and how we actually get gravitation from it. Um, in fact, I remember that in 2010 I was still in Paris, and I was finishing my PhD thesis, and I remember that Verlinde actually came to give a talk exactly on that topic. So I've got quite a bit of history with this as well. Anyway, so basically it has to do with the origin of gravity and the laws of Newton. As you're going to see, the angle that is kind of taken here is basically that of thermodynamics. So essentially, um, construing gravity as a sort of emergent thermodynamic phenomenon. And we are going to see in what sense it is kind of thermodynamical. So, blah, blah, blah. So, first of all, let me say as well, this paper has two parts. The first one gives an outline of the arguments, and the second part actually goes a bit more into why these arguments are going to hold, irrespective of the kind of microscopic theory you're going to put forward. Okay, so I'm going to focus here mostly on the first part and going quickly through the first part. And then, if you're interested in reading further, then the second part is accessible for free. I will put the paper, obviously, in the notes of the video. Okay, so here there is some basic stuff about the universality of gravity. Okay, so um, of all forces, gravity is clearly the most universal. It influences and is influenced by everything that carries an energy. Indeed, that's quite really special. If you look at the standard model of particle physics, you always have, oh, this kind of particle actually interacts with this and that, etc. But somehow it's like not all of them are interacting with each other. And indeed, gravitational forces appear to break that rule, and basically they interact essentially with everything. Um, there are things that are interesting and that people want to solve, and one of these is that gravity dominates at large distances but is very weak at small scales. And I think that's really a crucial point that people in particle physics are trying to address, and that's why they are looking for all these different ways of getting to gravity. This is also related to the fact that the quest for the unification of gravity, which is the forces of nature, is actually a big problem. Okay, so that's one of the many reasons. So there are plenty of reasons why essentially you would want to find new ways to think about gravity that basically will make much easier all of these current theoretical and conceptual issues involving gravity. So basically that's it. So there is some thing here. We are going to go further. So then the main idea here is going to be that of holographic principle. And what is meant here by the holographic principle, at least in general, is basically that uh, uh, so that's what is written here. The most important assumption will be that the information associated with a part of space obeys the holographic principle. So that's one thing. And then I think what is fascinating as well here is that, again, this is fairly accessible to many people because this is not like highly technical relativistic quantum field theory. This is essentially a sort of classical context that is being looked at. Um, and in fact, that's what is actually fascinating. Usually holography is studied, in relativity contexts. And Verlinde points out, however, the gravitational force is also present in our daily non-relativistic world. So indeed, we need to have an actual understanding of gravity, which is not relativistic. And that's what is aimed at here. Um, so just let me check. I want to find Um, I wanted to find there is a place somewhere where there is like what is going to take for holographic. Sorry, I had found it earlier. It doesn't matter. Like the whole point is that what they call kind of holographic principle is just to say that if you've got an enclosed volume, then there is a way to encode um, uh, at least a part, if not the entirety of the information enclosed in the volume at the border of that volume. That's kind of the underlying idea of the holographic principle. This is somewhere in this introduction paragraph, but I can't retrieve it. It's fine. Now, let's see what is the biggest idea here. And it has to do with a notion in thermodynamics which is called entropic forces. These are things that basically happen because of entropy and nothing else. So it means that it's not driven by real forces like the forces of the standard model. It's actually related to whether the entropy wants to go, where the entropy wants to go, if you will. So, for example, if you have some particles of ink that basically spread in a dilute that are diluted and spread in water, they are going to spread. Now they are going to spread, and this particular phenomenon is an irreversible process which is creating entropy. Okay, so it's producing entropy. Now, there is one way to actually leverage this to do work, and that is to actually put in the box, you put a semi-permeable membrane that let the actual water molecules, let's say if it's in water, let the water molecules pass through, but then the ink particles are much larger. Often they can be microns in size, and they are not let go. So as they are going to expand and basically explore the available space while increasing the entropy, they're also going to push this membrane and basically do work. Um, and basically that's kind of the idea. So entropy can be related to forces. The example given by Verlinde is that of the so-called um, entropic elasticity of a polymer. So if you imagine a polymer, so polymer like DNA, or so these are tiny, tiny, tiny little strings, molecular strings, that are assumed usually to be actually rigid. So they are made of rigid rods, if you will, and these rods can kind of move around and can rotate, etc., but they can't stretch. That's a traditional model. That's because we are looking really at covalent bondings. Of course, these covalent bonds can stretch under very, very strong force, but they can't stretch when you look at, let's say, forces that you exert typically on polymers. So we are not talking about bond breaking and bond stretching. We are talking about a form of elasticity that emerges from the fact that your polymer is made of multiple rods that are all stitched together to actually create a shape, a string, or a sort of snake-like structure. Now, what happens is that when you, and that's what is depicted on the figure here, if you anchor the one end of the polymer at on the wall, for example, and then you pull on it on the other end with a certain force, then the actual basically force you need to exert, if there is some temperature going on, is going to be linearly increasing with the distance you're moving away from the other end. Okay, and that's literally like a spring like force. In fact, eventually it doesn't become stringy anymore. It's actually a hyperbolic tension function, but there is a linear regime to it. Now, where does that particular force come from? Why is it that you need to actually exert a force to reach a certain separation between the endpoint and the initial point? And the reason why is because as you're stretching out the polymer, then its entropy is going to decrease, and this is not favored. Okay, so there is a counter-entropic force that is countering the force you're exerting on the polymer. Um, if you want to view that like the entropy counts the logarithm of the number of configurations available, then you realize that as soon as you stretch or try to separate the two ends of the polymer, then essentially you're going to restrict the number of configurations that are allowed, and in doing so, decreasing the entropy yet again. And so that's kind of the multiple ways you can look at it. But the bottom line is that this gives rise to an emergent, temperature dependent uh, force, basically when you try to stretch a polymer, which has nothing to do with the actual molecular composition of the polymer itself. It's a universal force that is going to exist. And this universality here is crucial to explain gravity. So so there is some further explanation here. You may want to read on this, but that's kind of the main idea that is going to be put forward here. Now, how do we make sense of this in the context of holography and so on? So the idea here has to do with borrowing from Bekenstein's argument when he came up with the entropy of a black hole. Okay, so if you imagine here that you've got some temperature T and you've got a surface which is a holographic surface. You can just imagine again, this is a sort of surface that has this property that somehow everything on the left-hand side, for example, of that surface is going to be encoded on the surface itself. Now, if you use Bekenstein argument, the idea was twofold. That if the particle is close enough, and close enough here was the quantum length, and we're going to come to that. So if the particle is essentially a sort of wavelength, because it's a quantum particle, it's a sort of wavelength away from the black hole horizon, that was the initial argument of Bekenstein, then the entropy of the black hole would be increased by an amount of 1 bit, and so the information would be increased by 1 bit, and therefore the entropy would be increased by kb log of 2. But if you use the binary logarithm, then you basically get the log 2 in base 2, and that's basically 1. Okay, and so that's what here it tries to describe by looking on the very left-hand side here. He says, well, imagine this surface here is basically, I'm looking very close to a black hole. So delta S is the entropy change. So if the particle is within delta X, which is h bar over mc, which is a quantum length, then basically I'm going to get this entropy variation. Now, the presupposition here is that if this is then an arbitrary distance away from that plane, then you should be having delta S would be 2 pi kb mc over h bar, and then times delta x, so a linear dependence in delta x. Now, there is some further discussion, if you want, to explain why this is acceptable to imagine a linear dependence in the position away from the plane, which is here assumed completely infinite. I will let you kind of have a read at this. But the bottom line here, then the force times delta x is interpreted as T delta S. Okay, so essentially you can define the force by the work, if you will, times that is equal to T delta S, the entropy change. So that's kind of the idea. Now you could say, okay, but what is the temperature I'm talking about? And here this is coming from again another phenomenon within cosmology and general relativity, which has to do with the so-called Unruh, I don't know exactly how to say that word, Unruh effect, which has to do with the equivalence between acceleration and basically any radiation, and but similarly acceleration and radiation with temperature. And therefore here you can actually define a temperature which is the acceleration of the particle here. And so if you actually basically follow this and then you apply that, you end up with finding F is equal to ma. That's kind of the bottom line. So you can retrieve F equal ma by having a simple reasoning based on Unruh's argument and based on the kind of holographic principle that was initially put forward by Bekenstein for its relation with entropy. Okay, so now let's have a look at the ideas of Newton's law of gravity. So how does Verlinde kind of put it? Well, he says, well, imagine that instead of having an actual plane, we have instead an actual sphere. So our holographic surface is a sphere, and it encodes whatever is inside of that sphere. Essentially, that's describing a black hole. And so here it uses again most of these things can be found by simple dimensional analysis, but essentially you can find kind of the number of bits that you can encode at the surface of that particular sphere, and that's the number given here, where A is the area of the sphere, C is the speed of light, G the gravitational constant. But again here, G would appear as a constant related to the information to the area, if you will. So that's how it would come from. It wouldn't come from gravitational stuff. It would come from a connection between area of a holographic surface and the number of bits that can be basically accommodated by that surface. And then what happens is that if you apply what we had seen before, alongside what is called the equipartition rule, then you end up essentially finding just here the force between a mass that would be at the center of the volume inside the holographic region, and then a particle of mass m that would be outside of that sphere. And you would find that this is gmm over r squared. So you retrieve that way the Newton's law of gravitation. And basically that's it. Now, of course, um, Verlinde is very candid here about what's going on. I mean, he does say that it's not really accident that we find this, because in fact, most of these things that he has been using were initially put forward from these particular laws of gravitation, etc. So here is simply reverse engineering the story, if you will. But in any case, what he says is that clearly the logic is different, and it may shed light into what gravity actually is. So um, changing the story in terms of where do you start from and what kind of story you tell is obviously going to change things a lot, especially when you think in terms of fundamental forces. And here he actually shows that you can have a sort of emergence of gravity in that case. Um, so as I said, the rest of the paper has to do with the naturalness and robustness of this derivation and so on. So I will leave you with this. And if you want to read further, you can. I thought it's a very interesting and very accessible paper to read. If you've got any criticism, questions or comments, by all means, do let me know in the comment section. And otherwise, see you in the next video.